All right, so I think this example is probably a little bit easier, but it sort of asks the inverse question, which is what is the pH of a buffer when you have given amounts of acid and base, some weak acid and conjugate base, or in this case weak base and its conjugate acid. And so the example uses tris. So tris is a really common buffer in biological systems. Several of you probably use this or at least have heard of this stuff. Super, super duper common for either making media or growing up cultures, amongst many other things, even protein purification in cases. So I, uh, I grabbed some information for you already, but if you didn't have that, which you wouldn't always, you may just, this is all you get, is what is the pH of a buffer with these two compounds. Um, Before you even do anything, you've got this thing, which is tris HCl, and you've got tris. You're probably going to want to look these things up and see what they look like, which is what I provided you here. This is just grabbed straight off of Google Images. But there's a dead giveaway with what you're dealing with here, and what is the base and what is the acid. Anytime you have a component where you have a compound and then it's bound to HCl, that's a dead giveaway that that's going to be a base. And that's really common, especially if you look at like pharmaceutical drugs, things you often take. A lot of times what you will get as a product in pill form for oral consumption will be some compound, and then it will say with a dot or a dash HCl next to it. Most drugs, surprisingly, are that way. What that really means, if you haven't seen that or learned about that, what that really means is in practice, via organic chemistry, if you have that compound and you have it dissolved as probably typically in an aqueous solution, you have it dissolved. If you add HCl to it, what you'll do is if there's an amine present, which there is here, this compound over here is tris, and this is sometimes people call this trish or tris HCl. They're the same thing. The compound over here, if we protonate this, right, we add the H plus via HCl, that turns it into this NH3, but it's charged as a plus. If you wanted to package this as a solid, obviously you can't just take an ion out of solution. You need to couple that with a counter ion, which is why you have the chloride. So when they talk about HCl being added, what they really mean is the protonated amine with chloride as the anion to form the salt. And the salt is the solid form that precipitates out and which you consume as a consumer. So what I got here are the two compounds, and you're given the two compounds in mass, in weight. So you're probably going to need to know the molecular weight of both of these things. So, you know, thinking through the process, this is what you'd have to do. You'd have to figure out what do these things mean. Okay, I've got the base and I've got the acid. This is a protonated base, so what that really means is I've got BH plus here, which is what is written here. So you've got the protonated form of the base, which is actually then the acid, and then tris is truly the base here, but the conjugate base. So this is just B. And so you've got this equilibrium where you've got BH plus and B plus H plus, where this is the tris HCl, this is the tris, and this is your H plus. So we're going to need to know the molecular weights of those things so we can figure out how many moles we have in each liter, and then of course we'll use the Henderson-Hasselbalch expression to compute what the final pH is. Okay, so I just tossed in some values for you so you don't have to look them up. So we've got the molecular weight of the tris HCl. That includes the mass of the chlorine, or the chloride in this case, plus the mass of the proton, the HCl. So it's really tris plus the mass of HCl. Gives us 157.597, and then the mass of just tris, which is 121.136 grams per mole. We're also given the pKa, that's here. We can just look that up. So 8.075. So what we need to do, since we have a pKa given to us, is we need to use the acid form of the Henderson-Hasselbalch equation, which is pKa, oh, sorry, getting ahead of myself here, pH equal to pKa plus log base over acid, and in this case, that means B over BH plus. That's the equivalent there. So to compute the pH, we'll toss in our pKa plus log, and what we're need to do is compute the moles and the molarity of each of them. Okay, so I just did some quick math and converted these masses of tris-HCl and tris using the molecular weight into moles divided by 1 conveniently gives me the molarities, or the concentrations, of both tris and tris-HCl in this buffer. So I can take those values, substitute them into my Henderson-Hasselbalch equation again with the base on top and the protonated form of the base on the bottom, or the acid. 8.075 is my pKa. I could solve this, and this gives me 8.61. So that's the pH of my system.